concentration of NO2 squared set over the concentration of nitrogen to the first power times the concentration of oxygen squared. Products over reactants, where the coefficients become the power. And the equilibrium constant, the magnitude of the number, gives us insight if we're favoring products or reactants. In relationships that describe equilibrium constant K in terms of a chemical equation, this is kind of leading into some Hess's law, where we could flip reactions, we can double them, and watch to see what happens to the equilibrium constant. So let's suppose when an equilibrium constant is written in the forward direction, we call it K, and all of a sudden we write that equation backwards. What's going to happen to the equilibrium constant? Well, if the forward reaction is read left to right, A plus B goes to C plus D, K forward will be the products over reactants, where we looked at C being times D set over A times B. But what happens if you read that backwards? For whatever reason, during a Hess's law experiment where we have to flip the direction, if we flip the direction, C plus D now becomes on the left and goes to A and B. So really, when I place products over reactants, we have flipped the direction. So therefore, I'm seeing the forward reaction and the reverse reaction, their equilibrium constants are being set equal to their reciprocal value. K forward is equal to 1 over backwards, or K backwards is equal to 1 over K forward. You can read that either way. But they are indeed reciprocals, 1 over the value. So if I know the K for the forward reaction, and I need to calculate the K for the reverse reaction, I'll set 1 over. I call that taking a reciprocal, and we would have the value. So flipping the direction, I take 1 over the value, take the reciprocal, and we'll have the new value. Suppose relationships continued here when the coefficients of an equation are multiplied by a factor, as we often do in Hess's law. If we have to double or take a half, what would we do to the equilibrium constant? Well, again, think about if just a generic, if A plus B goes to C. Notice here how we've got C raised to the coefficient, A raised to the coefficient. What if we double it? What if I have to distribute a 2 throughout this entire equation? For the reaction, 2 times the original coefficient plus 2 times the original coefficient of B now is twice that of C. Notice what's happened? We are actually using that distribution to square those coefficients down below. So whatever you're doing through that equation, you're going to end up doing that to the power, raising it to the power of that original coefficient. So if the original value here ended up to be squared, we're going to take that original equilibrium and end up squaring it to find the new. If you distributed a 3 through the coefficient, you'd have to cube the original value to find the new value. If you took 1/2 of the original concentrations, distributed a 1/2, you would raise it to the power of 1/2, which is the square root of the value. So distributing a coefficient raises it to the power of that very coefficient. So far we said A plus B goes to C, just to kind of keep our bearings. If A plus B is going to C, we get what's called an equilibrium constant. If you flip the direction, C is now going to A plus B, we know the new value would be 1 over the equilibrium constant. We take the reciprocal. Second example, we said, suppose our original value, A plus B goes to C. We have a number. But now I double it. 2A plus 2B goes to 2C. It's that original equilibrium squared. If I tripled A, B, and C, then I would cube. All right, so those are the 2 rules we know so far, kind of leading into some Hess's law. If I take the reverse, I take the reciprocal. If I distribute a coefficient, I'm going to square it or cube it or whatever that coefficient is that I distributed. I'm going to raise it to the power to find the new value. And finally, when you add equations together, as what Hess's law asks us to do, to get a third new equation, the equilibrium constant of the new equation is the product of the equilibrium constants of the old equations. When I add reactions together, I multiply their equilibrium constants. For the reaction A goes to B, and the reaction B goes to C, reaction 1 is going to be added to reaction 2. Now think about that in terms of Hess's law. If A goes to B and B goes to C, and I add those together, notice that B's will simplify, and the sum of those would be A goes to C. Equation 1 has a unique equilibrium constant. Equation 2 has a unique equilibrium constant. And if I'd like to find for the new equation after adding them together, I'm going to multiply. The new equilibrium constant will be found by multiplying K1 times K2. Simplifying the equation, but we multiply the K's. So let me repeat again, just to stress. If A plus B goes to C, and I have an equilibrium constant, I flip the direction, I take the reciprocal. That's rule 1. Flip the direction, take the reciprocal. Rule 2. If A plus B goes to C and has a value of an equilibrium constant. Suppose I'm going to distribute a 3 this time. I'm going to triple the values. So I distribute a 3 through that first equation. It's the original equation equilibrium constant cubed. Raise it to the power with which you distributed the coefficient. Rule 2. Rule 3, to emphasize, when I add equations together, I multiply the K constants to find the new value for the added equation. Those 3 things will let us figure out how to use Hess's law in terms of equilibrium constants. Here's an example that employs those very basic rules of Hess's law. Compute the equilibrium constant at 25 degrees for the reaction ammonia produces 0.5 nitrogens and 1.5 hydrogens. Again, those coefficients are now fractions simply because we're looking at mole numbers. 1 mole of ammonia is produced for half a mole of nitrogen reacting with 1.5 moles of hydrogen. So given here, we have a ratio of 1 to 3 makes 2. 1 nitrogen with 3 hydrogen forms 2 ammonia. That's the basic balanced equation with whole numbers. They have an equilibrium constant given to us, 3.7 times 10 to the 8th. Again, that's a very large number, so it's favoring the product side.